In December of 1995, one of the most powerful scientists in America bet his reputation on an empty patch of sky. His name was Robert Williams. He ran the institute that operates the Hubble Space Telescope, and the job came with a rare privilege. Every year, the director receives a personal slice of Hubble's observing time to spend on anything he chooses. No committees, no votes, his call alone. Astronomers around the world compete brutally for that telescope. Most of them apply, wait months, and get turned down. Every hour of Hubble's attention is worth a fortune, and any scientist alive could name the discovery they would chase with a single night on it. Williams took 10 days of that precious time, 10 full days, and pointed the telescope at nothing. He picked a spot near the handle of the Big Dipper, a patch of blackness about the size of a pinhead held out at arm's length, selected precisely because nothing was there. No bright stars, no known galaxies, nothing anyone had ever bothered to name. Colleagues warned him he was about to embarrass the whole observatory. If 10 days of the world's greatest telescope came back blank, the failure would carry his name, and he said so himself. That was exactly why he spent his own time, and nobody else's. For 10 days over Christmas, Hubble stared into that empty spot and drank whatever light was there. Then the images came back, and the empty patch of sky turned out to hold 3,000 galaxies. Let me slow down and describe what actually arrived on those screens in Baltimore, because the picture has earned it. 342 separate exposures, stacked into a single image, and scattered across that image, glowing out of a spot chosen for its emptiness, were spirals, ovals, smudges, streaks, and collisions. Nearly every object in the frame was a galaxy, each one a city of stars, some larger than our own Milky Way, some small and ragged, some so distant that their light had been travelling toward that camera for most of the history of the universe. 3,000 of them. In a pinhead of nothing, the team grasped the implication almost immediately, and it is the kind of implication that makes people sit down. That patch of sky was not special. It was chosen for being boring, which means every other pinhead of sky, in every direction, up, down, behind the Earth, behind the Sun, should hold roughly the same crowd. Millions of pinheads tile the sky. Run the multiplication and the numbers stop behaving like numbers. So tonight we ask the question that picture forces on anyone who looks at it honestly. How many stars exist in the universe? You can look up an answer right now. NASA will tell you that the observable universe, the whole volume of space whose light has had time to reach us, may hold up to a septillion stars. A septillion, that is a 1 followed by 24 zeros. And I will say it once so you can feel the size of it. 1 trillion stars. The figure gets printed in articles and repeated in classrooms, and it slides past most people without resistance. Because at that scale, who's checking? We are. That is the whole video. Because underneath that famous number sits an uncomfortable truth. Nobody has ever counted it. No telescope has ever seen a septillion stars. No survey has come close. Humanity's most powerful star mapping machine, a spacecraft we will meet shortly, has individually measured about 2 billion stars in its entire career. 2 billion against a claimed septillion. That gap is not a rounding error. That is a factor of 1 trillion standing between what we have actually counted and what we claim to know. So the septillion is not a measurement. It is a chain of reasoning. Link after link after link, stretching from your own eyes all the way out to the edge of everything visible. Some of those links are forged out of steel. Some of them, and the scientists who built them will tell you this themselves, still wobble. Tonight we take the chain apart, one link at a time. We will find out where each number comes from, who first worked it out, what it rests on, and how badly it could be wrong. When a link holds, we keep it. When a link bends, we say so out loud and fix the number right in front of you. By the end, you will know exactly how much of that septillion is evidence, how much is inference, and how much is honest, well-built estimation, and you will own something better than the number itself. You will know how a species that has counted 2 billion stars earned the right to talk about a trillion. To keep us honest along the way, a counter runs through this entire video. Think of it as the official ledger of the census. It opens tonight at the only figure we can truly defend. The stars our species has actually measured. One by one, you will watch that ledger grow and jump and once or twice explode. And every time it moves, I will show you exactly what moved it. Every census has to start somewhere, and ours starts in the most obvious place there is. Long before Hubble, before any telescope, before a single lens was ever ground, there was one instrument for counting stars, and you own 2 of them. They sit about 2 inches apart, just below your forehead, and I have some bad news about them. They have been lying to you your whole life. Drive west out of Austin, Texas, for about 7 hours, past the hill country, past the last big grocery store, past the point where your phone gives up, and you reach one of the darkest places left in America, Big Bend. People plan entire vacations around standing there at 2 in the morning with their heads tilted back. The sky delivers. On a clear, moonless night in Big Bend, the Milky Way rises over the desert like weather. It is bright enough to cast the faintest shadow. First-time visitors say the same thing so reliably that park rangers treat it as a running joke. They look up, go keyed for a moment, and then whisper. There must be millions of them. It feels like millions. It genuinely does. So let's count. Astronomers keep a complete catalogue of every star bright enough for a sharp-eyed human to see without help, from both hemispheres, under perfect conditions. The total comes to about 9,000. That is the entire inventory available to the naked human eye. Everything visible from Texas, plus everything visible from New Zealand, combined. And since the Earth blocks half the sky at any given moment, a person standing in that Big Bend darkness with perfect vision has access to maybe 4,500 stars, and realistically, with haze crowding the horizon, closer to 3,000. 3,000. A high school gym holds more people. Set that against the number from Chapter 1. NASA's septillion carries 24 zeros. Your eyes, on the best night of your life, in one of the darkest deserts on the continent, deliver a number with 4. The distance between those 2 figures, between the gym crowd and the trillion, is the exact distance this video has to travel. Every chapter from here forward is 1 step across that gap, before taking the first step. Though, we need to deal with the instrument itself, because the human eye is worse than limited. It is deceptive. It hands you a picture of the universe that is wrong in 3 specific ways, and each of those lies will haunt this census for the rest of the night. The first lie is that bright means big, or bright means close, or bright means important. By itself, it means none of those things. The brightest star in the entire sky is Sirius, blazing away every winter over every backyard in America. And Sirius is nothing special as stars go. It is a fairly ordinary star that happens to sit practically on top of us, about 8.5 light years out, which in galactic terms is the house next door. Meanwhile, some of the faint stars you can barely pull out of that Big Bend sky are monsters. Giants tens of thousands of times more luminous than the sun, so far away that their fury arrives as a whisper. Your eye ranks stars by appearance. The universe does not grade on appearance. Confusing those 2 things kept astronomy stuck for 2,000 years, and untangling them, separating how bright a star truly is from how bright it merely looks, will turn out to be the single key that unlocks the size of the universe later tonight. Hold on to this lie. It is the important one. The second lie is quieter. Your eye enforces a cutoff. Below a certain brightness, a star simply does not exist for you. No fading. No, maybe, a line. And under it, nothing. Those 9,000 stars are not a fair sample of the sky. They are the winners, the loudest voices in the room. Every one of them either unusually close or unusually powerful. The quiet majority, and it is an overwhelming majority, waits below your cutoff in total silence. Later tonight, when we finally meet the true population of our galaxy, you will find out how much of it was standing in that desert darkness the whole time, invisible on principle. The night sky is not the universe. It is the universe's upper class. And the third lie is one we told ourselves. For most people watching this, the 9,000 was never on the table to begin with. Roughly 4 out of 5 Americans live under skies so washed out by artificial light that the Milky Way has vanished entirely. From a typical suburb, you might catch a few hundred stars. From downtown Chicago, a few dozen. The most common human experience of the night sky today is a blank orange ceiling with Venus and a passing airliner. We built that ceiling ourselves in about a century, and it means the oldest starting point of any star census. The look up and count experience our species began with has quietly disappeared from most human lives without anyone voting on it. So this is the equipment humanity started with. An instrument that ranks the sky by appearance instead of truth. Deletes the majority of the population outright, and these days mostly points at streetlight glow. Every number in the rest of this video exists because somebody, somewhere, refused to accept those limits. If you enjoy investigations like this one, a quick like and subscribe genuinely helps the channel, which leaves a fair question on the table. Before telescopes existed, before anyone even knew what a star was, how far could sheer human stubbornness get with those 2 flawed instruments and endless patience? The answer is a specific number, and we know it exactly. Because 22 centuries ago, on a Greek island, a man wrote it down. The island of Rhodes, in the eastern Mediterranean, sometime around 130 years before Christ, a man named Hipparchus is doing something no one on Earth has ever done. He is writing down the sky, every star he can see, one entry at a time, its position, plotted against a grid he largely had to invent, its brightness, ranked on a scale he made up on the spot. Class 1 for the brightest stars down to Class 6 for the faintest his eyes could pull from the dark. No telescope, no clock worth the name, no photographs, no computers, no assistant checking the work. One man, a set of bronze sighting instruments, and years of nights. His finished catalogue held roughly 1,000 entries. Call it 1,026 stars. The count later astronomers attributed to the surviving version. That was the census of the universe. Complete, as far as any human could know. And that improvised brightness scale, Class 1 through Class 6, astronomers never threw it away. It became the magnitude system. And the data streaming out of our finest space telescopes tonight is still sorted on a ladder built by a man who died before Julius Caesar was born. For our investigation, one detail matters above the rest. Over the next 17 centuries, that number barely moved. Ptolemy repackaged the catalogue. Arab astronomers refined it, corrected it, and gave the stars the names we still use. Aldebaran, Rigel, Vega, better minds, better instruments, better math. The count stayed parked near 1,000. The sky was never the problem. The eye was. And every explosion in this census, every jump the ledger makes tonight, happens the same way. The stars hold still. The eye gets replaced. The first replacement arrived in the winter of 1610 in northern Italy, and it was about the length of a walking cane. Padua, January 610. A 45-year-old math professor with money problems and a side business making instruments has spent the autumn grinding glass. Galileo Galilei did not invent the telescope. A Dutch spectacle maker got there first, and the idea spread across Europe like gossip. What Galileo did was take a toy that magnified 3 times and rebuild it, lens by lens, until it magnified 20. Then he did the thing that separates him from every other person in Europe holding one of those tubes that winter. Everyone else pointed it at ships and church towers. He walked outside on a cold, clear night and aimed it straight up. What followed over the next few weeks is the fastest rewrite of reality in the history of science. The moon, supposedly a polished, perfect sphere, turned out to have mountains casting shadows. Jupiter turned out to have 4 little stars circling it like clockwork. And then he swung the tube toward the Milky Way. Appreciate what the Milky Way was before that night. Every civilization had stared at that glowing band, and every one of them explained it as a substance. Spilled milk from a goddess, a river of light, a seam in the dome of heaven. Aristotle filed it as a kind of atmospheric vapour, and for 2,000 years that answer more or less stood. It was a thing, a smear, a glow. Nobody imagined it was made of anything smaller, for the simple reason that no human eye can resolve it into parts. Galileo put his tube on it, and the smear shattered. Stars. The glow was stars, individual points, packed shoulder to shoulder in numbers that reportedly left him stunned at the eyepiece. Everywhere he steered the tube along that band, more of them poured into view. Faint ones between the bright ones, fainter ones between those, crowds behind crowds with no bottom in sight. He tried to do the responsible thing and count a sample. He picked the small region around Orion's belt and sword, a patch where the naked eye finds maybe a dozen stars on a good night. His tube showed him more than 500. He drew about 80, gave up on completeness, and wrote, with the frustration of a man whose subject refuses to hold still, that the quantity was beyond belief. He rushed it all into print within weeks. A slim book called Sidereus Nuncius, The Starry Messenger, published in March of 1610. It sold out almost instantly, and buried in its pages sits the sentence that earns this chapter its place in our census. The galaxy, he wrote, is nothing else but a mass of innumerable stars planted together in clusters. Innumerable. Sit with that word, because it is doing something sneaky. The greatest observer alive, holding the most powerful instrument on Earth, just looked at the sky and reported that the count has no answer. For 17 centuries the answer was 1,000. 1 winter later, the answer was more than anyone can count. The telescope did not add stars to the pile. It removed the flaw under the pile. And that is the lesson our investigation carries out of Padua. The lesson that will repeat all night. The count has never had a ceiling. It only ever has an instrument. And every instrument fails downward. Into crowds it cannot resolve. Whatever number your best tool gives you is not the population. It is the tool's confession of where it went blind. Astronomy spent the next 3 centuries proving that lesson on repeat. Jump forward 170 years to a back garden in Bath, England, and a man who took the lesson personally, William Herschel, a working musician turned obsessive telescope builder, constructed mirrors bigger than anything on Earth, then decided, with a straight face, to survey the entire visible universe by hand. His method was almost comically direct. Point the giant telescope at one strip of sky. Let the sky drift past the eyepiece. Count every star that crosses the field, out loud, while his sister Caroline sat at a desk below, recording the tallies by candlelight. He called it stargazing, night after night, year after year, strip after strip. The 2 of them counted stars the way a farmer counts fence posts, and by the end they had personally tallied hundreds of thousands and sketched, for the first time, the rough shape of the star system we live inside, one man's eyeball, one woman's ledger, and the first crude portrait of the galaxy. The count now stood in the hundreds of thousands, and everyone could feel it was still a flaw. Then photography arrived, and the eyeball itself got fired. This is the upgrade people underestimate. A human eye, even Herschel's, resets itself 30 times a second. It cannot save. A photographic plate does the one thing no living eye can do. It accumulates. Leave the shutter open for an hour, and the plate collects an hour of light, stacking faint photons into visible specks, pulling stars out of the darkness that no human being had ever seen or could ever see, no matter the telescope, because seeing them required patience measured in hours. By the late 1800s, observatories were running photographic surveys of the whole sky, and the plates came back crowded beyond anything Galileo dreamed. The count crossed into the millions, and the glass kept piling up, tens of thousands of plates, each one holding thousands of uncounted stars, which created a brand new problem, one no astronomer had ever faced. The bottleneck was no longer seeing the stars, it was counting what the plates had already seen. Someone had to work through that mountain of glass, star by star, measuring and cataloguing, and the male astronomers of the era considered the work beneath them. So Harvard College Observatory hired women to do it, dozens of them over the years, working in a single room, paid about 25 cents an hour, bent over glass plates with magnifying loops, measuring the brightness of star after star after star. The press called them Pickering's computers. After the director who hired them, management filed the work as clerical. It was anything but. Several of those women, staring at more stars than any humans had ever examined, began noticing patterns in the data that nobody upstairs had thought to look for. One of them, a minister's daughter from Massachusetts, nearly deaf, quiet, relentlessly precise, drew the tedious assignment of comparing plates of the same sky taken on different nights, hunting for stars that changed. Remember her. In a few chapters, that woman hands this census the single most important tool it will ever own. And I am not exaggerating when I say she is the reason we know the size of anything beyond our own galaxy. By the early 20th century, then, the ledger read like this: catalogued stars, in the millions and climbing, estimated stars in our system, hundreds of millions at minimum, clearly more. The word innumerable was starting to sound less like poetry and more like a project plan, and astronomers began saying out loud that a real census, a true count of the galaxy, would need something beyond plates and hired eyes. It would need a machine that could measure every star it saw, automatically, perfectly, billions of times over. They were right. Building it took about a century. It is flying right now, 1,000,000 miles from Earth, and it is the greatest counting machine our species has ever launched. 1,000,000 miles from Earth, 4 times farther out than the Moon. There is a quiet parking spot in space. Gravity from the Earth and the Sun balance there in a way that lets a spacecraft circle slowly around an empty point, keeping pace with our planet as it orbits, holding the Sun, the Earth, and the Moon all conveniently at its back. Astronomers call the spot L2, and we send our most delicate observatories there because it offers the two things precision work demands, deep cold, and a clear view of everything. In 2013, Europe parked a spacecraft there called Gaia, and gave it a job description 1 sentence long: measure the galaxy, measure. And that word is the whole chapter. Anyone can photograph the galaxy. Gaia was built to take its dimensions. The spacecraft looks like a spinning top, wearing a 10-foot sun shield for a skirt. And it does exactly one thing, with a monotony that would break a human mind. It rotates, slowly, once every 6 hours, sweeping 2 telescopes around the entire sky, over and over. Year after year, every star crossing its view gets clocked by a camera of nearly 1 billion pixels, the largest ever flown when it launched. Then the sky comes around again, and Gaia clocks every star again and again. Across its mission, Gaia has observed the sky so many times that its logbook holds trillions of individual measurements, and the average star in its catalogue has been visited hundreds of separate times. Why the obsessive repetition? Because Gaia is not collecting pictures, it is collecting motion, and motion is where distance hides. The trick at the heart of the machine is one you can run right now. Hold your thumb out at arm's length. Close your left eye and line your thumb up against the far wall. Now switch eyes. Your thumb jumps. It jumps because your two eyes look from two slightly different places. And the closer your thumb, the bigger the jump. That jump is called parallax. And it is the only truly honest ruler in astronomy, because it is nothing but geometry. No assumptions about what a star is made of. No guesses about how bright it ought to be. Two viewpoints and an angle. Gaia's two viewpoints are two positions of Earth's orbit. Opposite sides of the Sun. 186 million miles apart. It sights a star in January, again in July, and measures how far the star appears to shift against the deeper background. From that shift, high school trigonometry hands over the distance. The catch is the size of the shift. For a star 1,000 light years out, the angle Gaia has to detect compares to seeing a single human hair. Edge on, from more than 100 miles away. That is the measurement. That is what the spinning top at L2 performs. Hundreds of times per star, for roughly 2 billion stars, and distance. Once you finally own it, unlocks everything else. Recall lie number 1 from the Texas desert. The lie that brightness tells you nothing because you cannot separate a close ember from a distant bonfire. Distance snaps that lie in half. Know how bright a star appears, and know exactly how far away it sits. And you can compute how bright it truly is. Its real wattage. No illusions left. Add the star's colour, which Gaia records, and its drift through space, which Gaia clocks with the same patience, and each of those 2 billion points of light stops being a point of light. It becomes a filed, verified resident. This star, at this address, this luminous, this heavy, this old, moving in this direction at this speed. Gaia's catalogue is not a photo album. It is a census bureau's dream, the largest structured inventory of stars ever assembled, and working astronomers will spend the rest of this century mining it. So let's do what Chapter 1 promised and open the official ledger of this investigation. Stars individually measured, verified, and filed by humanity. As of tonight, about 2 billion. Give that number a moment, because it carries real weight. 2 billion is 1,000 times the count of the photographic plate era. It is 2 million times Hipparchus. Display Gaia's catalogue at 1 star per second. Day and night. No breaks. And you would stand there for over 60 years. Every entry measured to a precision bordering on the absurd. By one patient machine. Spinning in the cold. 1 million miles from home. By any honest accounting, it is the greatest counting achievement in human history. Now the question this chapter has been circling. 2 billion stars. Individually filed. What fraction of our own galaxy? 1 galaxy. The Milky Way alone. Do you suppose that covers? Take a guess. Most people land somewhere near half. The generous ones say most of it. The cautious ones say maybe a quarter. The answer is about 1%. 1%. The most powerful star-counting machine ever built. Running for over a decade. Executing the largest measurement campaign our species has ever attempted. Has personally met 1 star out of every 100 in its home galaxy. The other 99% have never been individually recorded by Gaia or by anything else we have ever flown. No file, no entry, no confirmed address. As far as direct measurement goes, 99% of the Milky Way is missing. And before you ask, no, this is not a budget problem or a patience problem. Run Gaia another 50 years and that percentage barely moves. Something else is going on. 3 things. Actually, built into the galaxy itself, standing between any counting machine and the population it is trying to count. Where exactly are the other 99% hiding? The answer is going to change how you picture your own galaxy for the rest of your life. Every summer, somewhere on Interstate 10 in West Texas, a dust storm rolls across the highway, and traffic does something instructive. It disappears. The cars are all still there, but stand at a rest stop and look down that highway, and you can watch the visible world shrink. The pickup 100 yards out is crisp. The semi behind it is a grey shape. The headlights behind the semi are faint smudges. Past that, nothing. The road runs on for 200 more miles, full of vehicles. Every one of them real. Every one of them gone from view. If your job was to count the traffic on Interstate 10 from that rest stop with binoculars, your count would fail. And it would fail through no fault of yours. The air itself was against you. Now, the fact that reframes your home galaxy, we live inside that dust storm, permanently. The Milky Way is not a clean spread of stars on black velvet. The space between its stars is littered with dust. And be precise about the word, because this is not house dust. It is soot and sand at the finest imaginable scale. Microscopic grains of carbon and silicates, particles smaller than the smoke off a struck match, breathed out over billions of years by dying stars. Spread thin. It seems like nothing. A cube of interstellar space the size of the Earth might hold a few pounds of it. But the galaxy is not small, and the sightlines are not short. Stack that almost nothing across tens of thousands of light years, and it becomes a wall, and our address makes it worse. The Milky Way is shaped like a pancake, a flat disk 100,000 light years across, with nearly all of its stars and nearly all of its dust packed into that thin plane. The sun sits inside the pancake, about halfway from the centre to the edge. Look up or down, out of the disk, and the view is fairly clean, but that view holds the fewest stars, the crowds, the dense star fields, the galactic downtown. All of it lies along the plane, and seeing any of it means looking edgewise through the thickest possible smear of dust. The direction with the most stars is precisely the direction we can least see. The census taker is locked in a windowless room in the middle of the city, with one clear hallway pointing at a cornfield. Nowhere does it sting more than toward the centre. The core of the Milky Way, 26,000 light-years away, is the densest gathering of stars in the entire galaxy. Measured honestly, the galactic centre should outshine the full moon in our sky. Instead, point at it from that dark Texas desert and you get a mild glow in Sagittarius. Pleasant and dim, the dust between here and there swallows the light of the galactic downtown almost completely. Invisible light, only about 1 photon in many billions survives the trip. The richest starfield we will ever live next to sits behind a wall. That is thief number 1. Dust. Thief number 2 operates even where the dust thins out. Picture photographing Times Square on New Year's Eve from a helicopter, then counting the crowd, face by face, from your photo, near the edges, where people stand apart. It works. Toward the centre of the frame, faces stop being faces. They merge into texture, a grain of humanity, and the count dissolves. Nothing is hiding anyone. There are simply more people per pixel than the camera can separate. Stars do the same thing. Gaia is a magnificent instrument, but every instrument has a resolution limit. The smallest angle, it can split into 2 separate objects. In the sparse neighbourhoods near the sun, Every star stands alone. Aim toward the rich star fields, the deep disk, the crowded clusters, the approaches to the core, and stars begin to overlap on the detector. 2 stars fuse into 1 dot. 5 stars fuse into 1 dot. In the densest fields, a single point of light in the catalogue may be an entire unresolved apartment building of stars, filed as one resident, and the crowding worsens exactly where the population peaks, which means the error is not random. The census undercounts precisely the neighbourhoods where most residents live. Thief number 3 is the one this whole video keeps circling back to. Faintness, the cut-off line from the Texas desert, the brightness below which a star stops existing for your eye. Gaia has a cut-off too. It sits spectacularly deeper than yours, millions of times fainter, but it is a line all the same. And most of the stars in the Milky Way, the overwhelming majority, are small, cool, dim stars that burn faintly even at close range. Move one a modest distance away, and it drops below Gaia's line and out of the census entirely. I am deliberately holding back just how extreme this gets. That reveal has its own chapter, and it earns it. For now, one sentence. The most common kind of star in the galaxy is a kind that almost never makes the catalogue. Dust, crowding, faintness. Stack the 3 thieves together, and the missing 99% stops being a mystery. Gaia has measured essentially everything measurable from where we sit. The rest are behind the wall, inside the crowd, or below the line, and no counting machine we could ever build, parked at this address, gets to meet them one by one. So what happens when direct counting hits a hard wall at 1%? You do what every census on Earth does when it cannot knock on every door, and mark this moment, because this is the exact spot in tonight's investigation where the method changes. Everything up to here has been counting. Everything from here on is inference. If this census has a load-bearing wall, we are standing on it now. The inference rests on 3 families of evidence, and none of them is guesswork. First, astronomers survey the clean neighbourhoods, the regions near the sun and the clear sightlines out of the disk, thoroughly enough to trust, and from those they learn the local recipe. How many dim stars accompany every bright one? Second, they chart the galaxy's true shape in kinds of light that beat the dust, infrared and radio, which slip through the smoke and reveal the disk, the arms, the crowded bar at the centre. Third, they weigh the whole thing, because every star orbits the galactic centre, and orbital speeds betray the mass doing the pulling. None of these roads stands alone. The shape constrains the model, the weight constrains the totals. The local recipe converts mass into head count, and each family of evidence checks the other 2. The way 3 witnesses lock down a story none could prove alone. Run it all together, and the answer comes out. The Milky Way contains somewhere between 100 billion and 400 billion stars. Update the ledger, and look closely at what just appeared on it, because the ledger has changed in kind. Not just in size, stars individually measured. About 2 billion stars in the Milky Way. Inferred 100 billion to 400 billion. For the first time tonight, the counter shows a range, and resist the urge to read that range as failure. That spread, that factor of 4, is honesty with a number attached. It exists mostly because of thief number 3, because the count of dim stars per bright star is still being argued at the edges, and every tweak of that recipe swings the total by tens of billions. The width of the range is the exact size of our ignorance. Published for anyone to check. Real science ships its error bars. Keep watching that range, because the question of the dim ones is not done with us. It comes back near the end of tonight to shake the biggest number we have. For now, take a breath and see how far the census has come. 9,000 stars by eye. 1,026 in the first catalogue. 2 billion measured by a machine 1,000,000 miles out, and now a full galactic estimate, 100 billion to 400 billion, built from surveys, physics, and cross-checked inference. The Milky Way, more or less accounted for. The logical next move practically writes itself. Find out how many galaxies exist. Multiply. Go home early. Except that move leans on an assumption so basic you probably have not noticed us making it. The assumption that anything exists beyond the Milky Way at all. That other galaxies are even real. And hear how strange this is. Within living memory, within the lifetime of people whose grandchildren are alive right now, that assumption was not a fact. It was one side of an open scientific fight. As late as 1920, the smartest astronomers on Earth could not agree on whether the universe contained many galaxies or exactly one. And the argument came to a head on a single spring evening, in a museum auditorium in Washington. D.C. Everything left in this census hangs on who was right in that room. April 26th, 1920. The Smithsonian's Natural History Museum on the National Mall. A Monday evening, and the auditorium is filling with the scientific establishment of the United States. The National Academy of Sciences is in session, and tonight's program carries a deceptively mild title, The Scale of the Universe. Two astronomers will speak. Depending on which one is right, reality is either one island of stars, or something so much larger that the word universe barely stretches to cover it. Speaking first, Harlow Shapley of Mount Wilson Observatory, 34 years old, a former Missouri farm boy who clawed his way into astronomy and arrives fresh off a genuine triumph. Using the great telescopes in California, he has just measured the true size of the Milky Way, and his results stunned everyone, including himself. The galaxy is enormous, hundreds of thousands of light years across by his reckoning, vastly bigger than anyone believed, with the sun nowhere near its centre. Shapley walks into that auditorium convinced that a galaxy this huge must be the whole show. One magnificent system of stars, wrapped in infinite empty space. As he sees it, the universe is the Milky Way. Speaking second, Heber Curtis of Lick Observatory, 47, a former classics professor who traded Latin for the sky and became one of the most respected observers in the country. Curtis has spent years photographing the strange objects at the centre of tonight's fight, and he has come to Washington to argue something that sounds, in 1920, almost like science fiction. Those objects are other Milky Ways, island universes, immensely far away, each a complete galaxy of its own, and the cosmos is filled with them beyond counting. The objects in question are the spiral nebulae. Everything hangs on what they actually are. So, picture the evidence both men share. For decades, telescopes and photographic plates have been collecting these things. Little glowing pinwheels scattered across the sky, thousands of them catalogued. The biggest and brightest, the great nebula in Andromeda, is faintly visible to your naked eye on a dark autumn night, a slim smudge like a thumbprint on glass. Through the largest telescopes it resolves into a majestic spiral of glowing haze. But no instrument on Earth can answer the only question that matters. How far away is it? Distance decides everything. If Andromeda sits inside or near the Milky Way, it is a modest cloud of gas, a local curiosity, and Shapley's one galaxy universe stands. If Andromeda lies far outside, then that smudge must be titanically large and bright to appear as it does across such a gulf, which makes it a full galaxy of billions of stars, which makes the thousands of other spirals galaxies too, which multiplies the universe by a factor no one can calculate. Same smudge on the same photograph, two readings of reality, separated by one missing number. Both men bring real ammunition, and both bring arguments that will turn out to be wrong, which is what makes the evening so human. Shapley points at a nova flare recently photographed inside Andromeda and runs the logic backward. If the spirals are entire galaxies at immense distances, that single flare would have to have briefly outshone hundreds of millions of suns. Ridiculous on its face, he argues. Nothing burns like that. He cannot know that such explosions are real, that stars genuinely detonate with exactly that violence, and that astronomers will one day call them supernovae. He also leans on a colleague's measurement, claiming the spirals can be seen rotating, which would place them close by. The measurement is simply wrong, but nobody in the room can prove it tonight. Curtis, for his part, reads the novae correctly as evidence of vast distance and calls the spirals galaxies, while defending a much too small Milky Way along the way. The evening itself is polite, denser, and, in conclusive, two respected scientists lay out incompatible universes. The audience files into the Washington night, and nothing is settled. Historians still argue over who technically came off better, and the honest scorecard says each man was right about the things the other got wrong. Shapley had our galaxy's size roughly right and the spirals wrong. Curtis had the spirals gloriously right and the galaxy's size wrong. But the scorecard is not why we came to this auditorium. We came for what the deadlock reveals, because it is the purest lesson in this entire investigation. The fight could not be settled that night, and the reason was not a shortage of brains. The brains in that room were as good as any alive. It was not a shortage of data. Both sides had stacks of photographs of the actual objects in question. The room lacked one tool, a ruler, a way to take the distance to a smudge of light that no parallax, no geometry, no instrument of any kind could reach. Without that ruler, the size of the universe was not a research question. It was a matter of taste. The greatest astronomers on Earth stood in front of photographs of billion-star galaxies and could not tell whether they were looking at something the size of a solar system or something the size of creation. Every number in the second half of this census, every galaxy count, every deep field, every estimate we build from here to the final answer, depends on the ruler those men did not have, and history was hiding a twist from everyone in that room. The ruler already existed. It had been discovered 8 years earlier, quietly, in a cluttered workroom in Cambridge, Massachusetts, and it was sitting in the published literature, partly overlooked, its full power not yet grasped. Its inventor was not at the debate. She was not famous. She held no faculty position, and she had never once been granted telescope time of her own. She was one of the women from Chapter 3, the computers, the 25-cent an hour plate examiners, the nearly deaf minister's daughter I told you to remember. Her name was Henrietta Swan Leavitt, and while the great men of astronomy argued about the size of the universe, she had already, patiently, and almost without anyone noticing, worked out how to measure it. Cambridge, Massachusetts. In the first years of the 20th century, a brick building on Garden Street, a workroom crowded with wooden desks, and on every desk, glass, photographic plates, 8 by 10 inches, each one a frozen piece of night sky holding thousands of stars. They arrive by the crate from Harvard's telescopes, including a station in the mountains of Peru that photographs the southern sky, the half of the universe that never rises over New England. The plates pile up faster than anyone can read them. Tens of thousands of sheets of glass, a library of the entire sky with no card catalogue. Reading them is the job of the women in this room. Henrietta Swan Leavitt sits at one of those desks. She is in her 30s, a minister's daughter from Massachusetts, college-educated in an era when that is rare for a woman, and profoundly hearing-impaired since an illness in her 20s. Colleagues describe the same person from every angle: serious, kind, quiet, and precise to a degree that borders on unsettling. The director has handed her one of the most tedious assignments in the building, and one of the hardest. Find the stars that change. In practice, that means taking 2 plates of the same patch of sky, photographed weeks apart, and laying one over the other, somewhere in those thousands of identical specks, a handful have shifted in brightness, swelling or fading on cycles of days or weeks. They are called variable stars, and hunting them by eye is proofreading two copies of a phone book against each other, name by name, looking for a few changed digits. Leavitt is better at it than anyone alive. Over her career, she will discover more than 2,400 variable stars, roughly half of all the variables known to humanity in her lifetime, one overlaid plate at a time. In the stacks from Peru, she finds the ones that change everything. They sit in the small Magellanic Cloud, a hazy patch of the far southern sky, and among its stars she keeps flagging variables of a particular breed called Cepheids, stars that pulse with a steady, repeating rhythm, brightening and dimming like a slow heartbeat, each one keeping its own fixed period with beautiful reliability. Some beat in a day or two, some take weeks per cycle. As her list grows, Leavitt notices something. The bright ones beat slowly, the faint ones beat fast, and it holds as a rule, plate after plate. She tabulates 25 of them, plots brightness against period, and the points fall onto a clean curve, a genuine law of nature sitting on her graph paper. In 1912, the result is published. The brighter the Cepheid, the longer its pulse, in a smooth mathematical relationship you can draw with one line. Why is that little graph the hinge of this entire investigation? Stay with me for 2 minutes. Because this is the best trick in all of astronomy, and it deserves an honest walkthrough. Go back to the first lie of the night sky, the one from the Texas desert. A light in the dark refuses to tell you whether it is a weak bulb up close or a lighthouse far away. Nothing in the light itself breaks the tie. That single ambiguity is why the men in the Washington auditorium were helpless. Every smudge in the sky carries the same riddle. Bright because mighty, or bright because near. Leavitt's Cepheids came with a gift. They all live in the same cloud. Whatever that cloud's distance is, every star inside it sits at roughly that same distance. The way everyone in a stadium across the valley is roughly the same distance from your porch. That shared distance works like a laboratory control. If one of her Cepheids looks 4 times brighter than another, it truly is 4 times more powerful, because distance is treating them all equally, which means her curve is a property of the stars themselves. The pulse tells you the power. Read the pulse, and the star confesses its actual output, a lighthouse that announces its own bulb rating, in a code anyone with a clock and a telescope can read. And once you know a star's true power, the riddle dies on the spot. Compare true brightness against apparent brightness, how strong the light really is against how weak it looks from here, and the gap between those two numbers hands you the distance. Physics has known that rule for centuries. Light fades with distance in an exact, calculable way. The missing ingredient was always the true brightness, and Leavitt found where the universe had written it down. In the rhythm. Find a Cepheid anywhere. Time its heartbeat with a calendar, and you can compute how far away it is. Compute. With arithmetic. To an address no ruler had ever reached. Astronomers soon calibrated her relationship, anchoring the nearby end of the scale. And from that point forward, humanity owned something it had never possessed. A tape measure that reaches beyond geometry. Parallax. Our thumb jump from the Gaia chapter dies out after a few thousand light years, the angles shrinking below anything measurable. Leavitt's ruler has no such leash. Wherever a Cepheid can be photographed, distance can be taken, and Cepheids are luminous beasts, visible from enormously far away. You can see where this must go. The spiral nebulae, the smudges that deadlocked the finest minds in America. If anyone could find a single Cepheid inside one of them, time its pulse, and run Leavitt's arithmetic, the great debate would end in an afternoon, settled by procedure, the way arguments are supposed to end. Leavitt never got to run the procedure herself. Harvard kept her on plate work, measuring and cataloguing for hourly wages. She was never granted her own telescope time, never sent to chase her law across the sky, and she died of cancer in 1921 at 53, quietly, without the scientific world grasping what it had lost. A few years later, a member of the Swedish Academy began paperwork to nominate her for the Nobel Prize, wrote to Harvard for details about her research, and learned in reply that she had been dead for years. The prize cannot go to the dead. The paperwork stopped there. One more scene before we leave Cambridge. Years afterward, the astronomer Cecilia Payne, another woman who fought her way into that same observatory, remembered Leavitt's desk. Because of her deafness, colleagues often communicated with her in writing, and Payne recalled the little stacks of paper, questions and answers, the quiet machinery of a person the institution never thought to promote, building, in the margins of clerical work, the most consequential measuring device in the history of astronomy. The ruler existed. It sat in the published literature, waiting for someone with the nerve, the patience, and the biggest telescope on Earth, willing to aim it at the Andromeda Nebula night after night and hunt through millions of stars for one that pulsed. That someone was working on a mountain in Southern California, and in October of 1923, on a photographic plate exposed in the freezing dark, he found what he was looking for, crossed out his own first guess, and wrote 3 letters that ended one universe and started another. Mount Wilson rises 5,700 feet over Pasadena, California, and in 1923 the road up is a dirt track with hairpin turns that mules handle better than trucks. At the top, above the lights of Los Angeles, sits the largest telescope on planet Earth, the Hooker telescope, with a mirror 100 inches across, 4.5 tons of glass, so massive it rides on bearings that float on liquid mercury. On a clear night it gathers more light than any instrument our species has ever pointed at the sky. The man who books more nights on it than almost anyone is 33 years old, stands over 6 feet tall, smokes a pipe, and speaks with a British accent he picked up at Oxford and never put down. Edwin Hubble, Missouri-born, a former college athlete who promised his dying father he would study law, did so, hated it, and walked away for astronomy. Colleagues find him arrogant, distant, hard to love. History will find him something else. Thorough, Hubble's obsession is the spiral nebulae, the very smudges that deadlocked Washington 3 years earlier. His plan carries no cleverness at all, and that is its genius. Photograph Andromeda, the biggest spiral in the sky, through the biggest telescope on Earth, over and over, night after freezing night, and comb the plates for stars that change. He is hunting novae, flaring stars, anything whose behaviour might betray the nebula's distance. What he truly wants, what everyone who understands Leavitt's law wants, is a Cepheid, the perfect distance beacon, ticking away inside the one object that could settle the size of the universe. The nights up there are brutal in a way modern astronomy has forgotten. The dome is unheated, because heated air shimmers and ruins the images. The observer rides a platform in the dark, physically guiding the telescope through the entire exposure. 40 minutes, an hour, hands going numb, breath fogging, one eye pressed to the guide scope, holding a single star dead center while the great mirror drinks light. All night. Develop the glass in the morning. Compare it against last month's plates. Speck be speck. Thousands of stars, hunting for one that moved. On the night of October 5th into the early hours of October 6th, 1923, Hubble takes a 45-minute exposure of Andromeda on plate number H335H. The air is unsteady that night. The seeing poor. It does not matter. Examining the plate, he finds what look like 3 new flaring stars. He marks each with a small letter N. For nova, and files the result. 3 novae in 1 exposure. A good night. Back in his office, he does the thing that made him Hubble. He pulls the archive. Every previous plate of that region, some going back years, and traces each of his 3 novae backward through time. 2 behave exactly as novae should. There, then gone. The 3rd one is misbehaving. It shows up on older plates, then vanishes, then shows up again. Faint, bright, faint, bright, across months of archived glass. And the pattern is anything but random. It repeats. Hubble times the cycle and gets a period of about 31 days. A slow, steady heartbeat. And exactly one kind of star beats like that. He is looking at no explosion. He is looking at a pulse. A Cephite. Alive and ticking. Inside the Andromeda Nebula. And on the plate, in that moment, he makes the most famous correction in the history of science. He crosses out the N. Beside it, in red ink, he writes var for variable. And then, because he is a human being and he knows exactly what he is holding, he adds an exclamation point. Var. That plate still exists. Photographs of it are 1 search away from you right now. A grey field of speckled stars. A small crossed-out letter. 3 red letters and a punctuation mark. Written by a man alone in an office who has just become the only person on Earth holding the size of the universe in his hands. Because from here, it is arithmetic. Leavitt's law takes the 31-day period and hands back the star's true power. The true power, set against how faint the star appears from Earth, hands back the distance. And the distance comes out around 1 million light-years. 1 million. Shapley's Milky Way. The giant version. The one he used to argue that our galaxy was everything. Tops out around 300,000 light-years. The pulsing star sits far beyond the farthest edge of the most generous map of the Milky Way ever drawn. Which means the nebula holding it is a separate system entirely. A whole other galaxy of billions of stars. And the thumbprint smudge you can spot with your naked eye on an autumn night is the combined glow of another island universe. The great debate is over, settled by a heartbeat and a calendar. Hubble mails the news to Shapley in early 1924. Shapley, the champion of the one galaxy universe, reads the letter in his Harvard office, and by the account of a student who was in the room, holds it out and says, "Here is the letter that destroyed my universe." Notice what that sentence is, because it is science working exactly as advertised. Confronted with a measurement, the man who was wrong said so. Out loud, almost immediately, his universe was undone by a single pulsing star, timed with a calendar, run through a law discovered by a woman his own observatory had kept on clerical wages. Now watch the dominoes, because they fall fast. If Andromeda is a galaxy, what about the rest of the spirals? The thousands of catalogued pinwheels. Astronomers went down the list, and the verdict kept coming back the same. The spiral nebulae, one after another, proved to be galaxies, strewn in every direction, as deep as the plates could reach. Within a few years, the universe of 1920, one island of stars wrapped in infinite nothing, was gone, replaced by a cosmos in which the Milky Way is one system among multitudes, and the sky's faint smudges outnumber its visible stars. Stop and update the ledger, because the counter just made the single largest jump it will ever make. Before this chapter, our census read, stars in the Milky Way, 100 billion to 400 billion. That was a count of everything, because the Milky Way was everything. As of plate H, 335H, that same number is demoted to a unit. One galaxy's worth. The new question, the question the rest of this video lives inside, is how many of those units exist. And the honest answer in 1924 is that nobody has the faintest idea The plates show spirals as deep as anyone can photograph, with no bottom in sight. Galileo broke the floor under the count of stars. Hubble broke the floor under the count of galaxies. Our ledger does not need a new number tonight. It needs a new column. Filling that column took 70 more years. A telescope named after the man with the red ink, and a director willing to gamble 10 days of it on an empty patch of sky. You watch that gamble pay off at the top of this video. 3,000 galaxies in a pinhead of nothing. What you have not seen is how one crowded photograph becomes a count for the entire sky, and what that photograph was quietly hiding, even from the people who took it. Back to Baltimore. This time we read the deep field properly. Pull the picture back up. The one from the opening of this video. 10 days of Hubble's time. A pinhead of empty sky near the Big Dipper. 3,000 galaxies. We looked at it once the way the newspapers looked at it, as a gamble that paid off. This chapter, we read it the way the scientists read it. And I will tell you the mood of this chapter up front. Confidence. For the next few minutes, everything works. Turning one photograph into a number for the entire sky is a procedure, with steps. And tonight, we walk the steps and watch each one hold. Step 1. Throw out the imposters. Scattered across the deep field are a handful of objects that do not belong in the count at all, and you can spot them yourself once you know the tell. A few points of light in that image wear spikes, little crosses of light radiating from a bright centre, like stars drawn by a child. Those spikes are a fingerprint. They come from light bending around the support struts inside the telescope itself, and only one kind of object is close enough and concentrated enough to produce them. Stars. Our stars. Milky Way residents. Sitting a few hundred or a few thousand light years from Earth. Photobombing a portrait of the edge of the universe. They are raindrops on the window. And the first job is to flag every one and set it aside. In the original deep field, galaxies outnumber those foreground stars by roughly 100 to 1, which is its own quiet astonishment. Point a good enough camera at nothing, and almost everything you catch is a galaxy. Step 2. Certify the sample. The entire logic of the deep field rests on one claim, that this pinhead of sky is ordinary, boring, representative. If the patch happened to be unusually rich, some cosmic downtown, the multiplication would inflate the universe. If it happened to be a void, the multiplication would starve it. So, how do you certify boring? You run the experiment again somewhere else. A few years after the first deep field, Hubble stared down a second patch, a widely separated field in the far southern sky, chosen by the same rules. Nothing bright, nothing known, nothing special. If the universe had a grain, if one direction ran fundamentally richer than another, two distant pinheads should disagree. They agreed. Galaxy counts, types, colours, the whole census profile. Statistically, the same crowd in both fields. Any single small patch still carries some luck of the draw. A little more structure here, a little less there. Which is why astronomers pile up many fields and wide surveys before trusting the average. And the average keeps testifying to the same verdict. On the largest scales, the universe is monotonous. Whichever direction you drill, you strike roughly the same density of galaxies. Cosmologists elevate this to a principle, and it is the load-bearing assumption under everything tonight. So hear it plainly. We can multiply a pinhead into a universe only because the universe, at wholesale scale, appears to be the same stuff everywhere. It is the single most convenient fact our species has ever discovered, and it has survived every test thrown at it. Step 3. Multiply. Carefully. The arithmetic itself is almost embarrassingly simple. The first deep field covered roughly 1/24 millionth of the full sky. 3,000 galaxies in the patch. 24 million patches to tile the celestial sphere. Multiply, and you land in the tens of billions of galaxies. Then the deeper campaigns sharpen the figure. In 2003 and 2004, Hubble stared at another tiny southern patch for roughly 1,000,000 seconds. 11 days of accumulated exposure, producing the ultra-deep field. 10,000 galaxies in a speck of sky, smaller than the first one. Same procedure, deeper flaw, and the estimate climbs comfortably past 100 billion galaxies within reach of Hubble-class instruments. So there is a number, and it is a good one. 100 billion galaxies. Going on 200 billion. For about a decade. That was the textbook answer. And plenty of people watching this grew up hearing it. The procedure works. The steps hold. The confidence is earned. And yet, you have been with this investigation long enough to feel the question forming on its own. Every instrument fails downward. Galileo's tube had a flaw. Gaia has a flaw. So, 1,000,000 seconds of Hubble's attention, the deepest sustained stare in the history of optical astronomy, has a flaw too. Below some faintness, a galaxy leaves no mark even on that image. The ultra-deep field is a photograph of everything in that direction above a line, which sets up the next chapter's problem in one sentence. How much of the universe lives below the line? In 2016, a team led by the astronomer Christopher Consolis went after exactly that question, with a method you are about to recognize, and their conclusion made headlines around the world. The observable universe likely holds around 2 trillion galaxies, 10 times the textbook figure, 9 out of every 10 galaxies. By that estimate, had never appeared in any photograph taken by anyone. They were counted without ever being seen. Counted without being seen. That phrase should make you sit forward. And it should also make you a little suspicious. Good. Suspicion is the next chapter's job, because the method behind that 2 trillion is one of the oldest tricks in field science. It was perfected far from any telescope, and the best way to understand it involves a lake, a net, and a very patient biologist. But first, a short detour, because in the middle of all this careful statistics, the universe occasionally does something outrageous. Every so often, it hands us a magnifying glass and lets us see, directly, a single object below every flaw we own. It happened, spectacularly, and the thing that swam up out of the darkness was not a galaxy, it was one star. In 2022, astronomers announced that the Hubble Space Telescope had photographed a single star so distant that its light left home when the universe was less than 1 billion years old. Read that again slowly. A star, one star, seen across nearly 13 billion years of travel time. By every rule this video has laid down, that should be flatly impossible. At such distances, entire galaxies blur into faint smears. A lone star, even a giant, should be billions of times too faint for any telescope we have ever built or seriously proposed. The flaw is the flaw, unless something bends the flaw. Between us and that star sits an enormous cluster of galaxies, thousands of them bound together, a structure so massive that it warps the space around it. Exactly as Einstein said mass must. Light from behind the cluster does not pass in straight lines. The paths curve. The cluster behaves like a colossal, lumpy lens hanging in the sky, and here and there, by pure geometric accident, that lens focuses. The star happened to sit almost perfectly on one of those focus lines. Its light arrived at Hubble magnified thousands of times, boosted from hopelessly invisible to barely detectable. A firefly held up to a telescope by the gravity of 1,000 galaxies. The discoverers named it Earendel, an Old English word for morning star. The James Webb telescope later took its own look and teased the light apart, finding the signature of a massive, blazing blue star, possibly with a smaller companion, shining from an era when the universe was 1/20th of its current age. Carry Earendel with you for the rest of tonight, because this little detour hauls 2 cargoes. First, the wonderful one, The universe itself sometimes lends us an instrument better than anything we can build. And every time it does, there is something down there, below our floor, waiting. Second, the unsettling one. It took a once-in-a-sky alignment, a natural lens of galactic scale, plus our finest telescope, to see one single resident of the early universe. Everything else at that depth, every unlensed star, every modest galaxy, stays below the line, invisible on principle, countable only by inference, which is exactly the claim we left hanging. 2 trillion galaxies, most of them never photographed. Time to find out how anyone dares to count what the camera missed. Fair warning about this chapter. The last one was about confidence. This one is about doubt. The useful kind. The kind with instruments attached. By the end of it, the biggest galaxy number in the census will be standing trial. Start at a lake. Because there is a job in wildlife management that sounds made up, is completely real, and happens to be one of the most mathematically serious jobs in America. Counting the fish in a lake. Think the problem through honestly. You cannot drain the lake. You cannot interview the fish. All you can do is sample, and every sampling tool you own is biased. Run a net across the lake, and the net has a mesh size. Every fish bigger than the mesh gets caught and counted. Every fish smaller than the mesh swims through and, as far as your clipboard knows, does not exist. Haul in the net, count 200 base, and write down 200 fish. And you have not measured the lake. You have measured your net. Fisheries biologists cracked this generations ago, and their fix is the same one astronomy uses. So watch it work in the water first. Take one small cove and study it exhaustively. Fine mesh, electrofishing, direct survey, whatever it takes to genuinely count everything in that single cove, down to the fry. From that exhaustive patch, you learn the population's shape. For every big base, so many mid-sized perch, so many small bluegill, and a cloud of minnows. That ratio, big to small, unlocks the whole lake. Count the big fish everywhere. Apply the shape, and you can estimate the minnows you never caught, because the cove told you how many minnows swim beneath every base. That is the entire method. Study a small region completely, learn the shape, then correct the big survey for everything below its mesh. Astronomers even talk this bluntly. They speak of survey completeness, of correcting for what the instrument cannot reach, and the shape itself, the ratio of faint galaxies to bright ones, is one of the most carefully measured curves in the science. Entire careers live on its faint end, for exactly the reason entire fisheries careers live on minnows. The small ones dominate the count. This is precisely what the Consolis team did to reach 2 trillion. Hubble's deep fields were the net hauls. Nearby, thoroughly surveyed volumes of space served as the cove, revealing how many dim dwarf galaxies accompany every bright spiral in a given chunk of universe. Apply that shape to the deep fields, extend it below Hubble's mesh, and the 2 trillion emerges, most of it minnows, small, faint, and everywhere. Now let the doubt in, because a fair listener should be squirming, and the squirm deserves respect. The whole correction hangs on one assumption, that the shape measured in the cove holds out in the deep lake. What if it does not? What if the faint end bends somewhere below the mesh, and the minnows thin out, or multiply, in ways the nearby universe never warned us about? That is a real vulnerability, and it is the exact seam along which 2 trillion has been challenged. So the field did what good science does with a load-bearing assumption. It attacked from independent directions, and the 2 best attacks are worth your time, because each is a beautiful piece of lateral thinking. The first attack you have already met. Gravitational lensing. Every so often, as with Arundel, A massive cluster bends space into a natural magnifier and lets us look below our own mesh. No extrapolation. Just direct viewing of a region the statistics claim to describe. Astronomers deliberately aim deep surveys through these clusters, treating them as free telescope upgrades, and the little galaxies revealed in those lensed windows can be checked against the predicted shape. The dim population is not hypothetical. Through the lenses, we see the minnows. The second attack is my favourite measurement in this entire video, because it required no telescope pointing at anything in particular. It asked a childlike question with a savage edge. How dark is the sky? Really, every galaxy that has ever shined, catalogued or not, above the mesh or below it, contributes photons to the general glow of deep space. So the total darkness of the sky is itself a census, one that automatically includes everything, because light does not care whether we filed it. The trouble is that near Earth, sunlight scattered off interplanetary dust drowns that faint total glow, so researchers turn to the one camera far enough away to escape the glare, the instrument aboard the New Horizons spacecraft, the probe that flew past Pluto. By then cruising through the outer darkness of the solar system, they aimed it at empty sky and measured, as close as humanity has ever come, the true brightness of the void. The result carried a sting. The glow they found was modest, close to what the already catalogued galaxy populations can account for, leaving little room for vast hidden crowds of additional shining galaxies. Now, be precise about what that measurement can and cannot say, because the logic matters. Darkness limits light, and light limits the hidden. A huge population of extra galaxies can hide from cameras, but its combined glow still has to fit inside the measured darkness. And the darkness came back stingy. Galaxies that shine near the levels the 2 trillion projection assumes run into that ceiling. The measurement pressures the high count hard, though it cannot by itself rule out swarms of galaxies so faint they contribute almost no light at all. Researchers reading the New Horizons result have argued the totals it favours sit in the hundreds of billions. And the argument between that reading and the 2 trillion projection is alive in the journals right now. So where does the count stand tonight? Between the deep field statistics pushing high and the darkness of the sky pressing down, the defensible range for galaxies in the observable universe runs from a couple hundred billion up toward 2 trillion. And notice what the disagreement is actually about, because it is the healthiest kind. Both camps agree on the bright galaxies. Both camps agree dim galaxies exist in enormous numbers. The entire fight is the shape of the bottom of the net. 2 independent instruments. One staring, one integrating, bracketing the truth between them. That is a census mid-stride, doubting itself in public, with error bars instead of slogans. Update the ledger. Galaxies in the observable universe. 200 billion to 2 trillion. And now stare at the next step of the arithmetic. The step every version of the famous multiplication depends on. Take the galaxy count. Multiply by the stars in a typical galaxy. And the answer falls out. One small problem. Every documentary you have ever watched, every diagram you have ever seen, quietly slots the Milky Way into that sentence as the typical galaxy. Hundreds of billions of stars, grand spiral arms, the works. The Milky Way is about as typical as a Manhattan Tower, and the real average galaxy in this universe is something most people have never once seen a picture of. This chapter runs on surprise, so let's earn one immediately. Try a quick exercise with me. Calculate the average building in the United States. Your brain just pictured something. A 2-story house. Maybe. Or a small office block. Now actually run the inventory. The country holds a handful of skyscrapers, thousands of high-rises, hundreds of thousands of warehouses and schools and churches, tens of millions of houses, and then, way out past all of that, an absolute ocean of small structures nobody thinks to picture, tool sheds, barns, cabins, roadside stands, bus shelters. Count every roofed structure in America, and the towers become a rounding error. The skyline is not the country. The country, by the numbers, is sheds. Now here is the con that every space documentary, including plenty of good ones, has quietly run on you for decades. When the script says the word galaxy, the screen shows you a skyscraper, a grand glowing spiral, arms sweeping, hundreds of billions of stars, the Milky Way, or Andromeda, or something even bigger. And when the famous multiplication gets performed, galaxies times stars per galaxy, the number slotted in for stars per galaxy is a skyscraper number, 100 billion or more, as if every galaxy in the universe were built like ours. Almost none of them are. The Milky Way is a downtown tower, and the universe, like the country, is mostly sheds. Meet the sheds, because they are genuinely strange objects, and the fact that most people have never seen a picture of one is itself part of tonight's story. They are called dwarf galaxies, and the name undersells them. A dwarf galaxy might hold a few tens of millions of stars, or a few billion, against our hundreds of billions. Many have no elegant spiral structure at all, just a loose swarm of stars, dim, diffuse, and shapeless, like a handful of glitter thrown across black paper. The dimmest ones, and this is no exaggeration, are so faint that a single bright star in our own galaxy can outshine them. There are entire galaxies whose total light output loses to one supergiant star. That is what most of the universe's galaxies actually look like. No postcard, no screensaver, a faint smudge that a survey algorithm has to be carefully trained not to dismiss as a flaw on the image. How do we know they dominate? Because we can count them right here at home, in the one place where even the faintest sheds cannot hide, our own front yard. The Milky Way does not travel alone. It is orbited by an entourage of satellite galaxies, and the tally keeps growing. Decades ago, we knew of about a dozen. Then the sky surveys got deeper and more systematic, and the count of known satellites climbed past 50, with new ones still turning up. Some so sparse they were only recognized as galaxies by the coordinated drift of their handful of stars. Andromeda hauls a comparable swarm. Every giant galaxy we can inspect closely turns out to be a tower standing in a parking lot full of sheds, and the pattern repeats at every scale we can check. Bright galaxies are rare. Faint galaxies are common. The fainter you look, the more of them there are. The same relentless slope from the lake. The crowd always thickening downward. So the honest multiplication cannot be galaxy count times Milky Way. That would be estimating America's population by counting buildings and assuming every building is a Manhattan tower. The honest method is the bookkeeping you already know. Weigh the whole inventory by class. A vast crowd of small galaxies contributing a few million or billion stars apiece. A middle class contributing more. A rare heavyweight class contributing enormously. At the top of the scale, and they belong in this census because their existence is barely believable, sit the giant ellipticals, galaxies that grew by devouring their neighbours, colossal balls of ancient stars squatting in the cores of galaxy clusters. The largest confirmed ones hold on the order of 100 trillion stars each. One such galaxy carries the star count of nearly 1,000 Milky Ways. The full inventory of the universe runs from galaxies a single star can outshine, up to galaxies that outweigh 1,000 of ours. Averaging across that is not a matter of picking a nice round number. It is accounting, and now the turn this chapter has been saving. Because it is a genuinely pleasant surprise in an investigation that has spent most of tonight taking numbers away from you. Do the accounting properly, and something elegant happens. The sheds, for all their overwhelming head count, are small. It takes hundreds of dwarf galaxies to match the stars of one Milky Way. And the universe, numerous as its dwarfs are, does not stock quite enough of them to overturn the giants. Meanwhile, the towers, rare as they are enormous. Multiply each class by its population and add the columns, and the total number of stars comes out dominated by the big and middleweight galaxies, with the vast crowd of dwarfs adding a modest slice on top. The result lands in the same territory as the crude classroom multiplication. 100 billion galaxies worth of 100 billion stars, give or take the factors we have been tracking all night, which tells you something worth knowing about that famous back-of-the-envelope number. It was never rigorous. It skipped the dwarfs, ignored the ellipticals, and pretended our tower was a typical building. Then it landed in the right neighbourhood anyway, because its two errors, overcounting the typical galaxy while undercounting the galaxy population, partially cancel. The universe was kind to the lazy math. Tonight you know what the lazy math never knew, which is why it works, and exactly which assumptions it got away with. So the galaxy side of the census stands as honest as we can make it. 200 billion to 2 trillion galaxies, weighed by class. Giants, counted as giants. Sheds counted as sheds. What remains is the other half of the multiplication, the stars inside those galaxies. And for that we mostly cannot count heads. A galaxy at 40 million light-years is not a collection of resolvable stars. It is a glow, and the census has to convert glow into population. That conversion hides the biggest lie your eyes have ever told you. A lie about who the universe is actually made of. Because the light of a galaxy turns out to be a wildly dishonest witness to its own population. And the residents doing almost all of the shining are almost none of the residents. The real majority has been sitting in the dark this entire video. Time you met them. Everything you learned tonight is about to flip over. So brace for it properly. Do something for me. Picture a star. Right now, before I can bias you, hold the image. I can tell you, with unfair confidence, roughly what you pictured. Something like the sun, a blazing yellow-white sphere, maybe bigger, maybe bluer, roaring away in the dark. Every star on every movie poster, every star in every textbook diagram, every star your mind reaches for by default, lives in that family. Bright, hot, substantial. Now meet the actual universe. Line up 100 randomly chosen stars from the Milky Way. A fair sample, drawn by lottery. No favoritism. Somewhere around 75 of those 100 belong to a single breed, and it is nowhere near the sun's breed. They are called red dwarfs, and they are the overwhelming, monotonous, invisible majority of all stars in existence. A red dwarf is a star built on the smallest budget nature allows. Take between about 8% and half of the sun's mass. Compress it until fusion barely lights, and you get a small, cool, stingy ember of a star, glowing deep orange-red, often putting out less than 1% of the sun's light. Sometimes a 50th of 1%. They are no rare curiosity. They are the standard model, the universe's default setting for star, the economy sedan of creation. Manufactured in staggering numbers everywhere, stars form it all. And now, the fact that reframes every night sky you have ever stood under. Of all the red dwarfs in the entire heavens, all the countless billions in our galaxy alone, the number visible to your naked eye is 0. 0. No exceptions. No desert dark enough. No night clear enough. Every single red dwarf in the universe sits below the brightness cutoff of human vision. 3/4 of the stellar population of the cosmos, and no unaided human eye in the history of our species has ever seen even one of them. The most common kind of star in existence is a kind of star that, as far as direct human experience goes, does not exist. Want the sharpest version, the closest star to our solar system, our literal next-door neighbour, is a red dwarf called Proxima Centauri. It sits 4.25 light-years away, which by galactic standards is touching distance. It is the nearest star any human will ever have, the first stop on any journey outward. And you cannot see it. Nobody can. Even under an exceptionally dark sky, Proxima runs roughly 100 times too faint for the unaided human eye, hanging invisibly in the southern sky beside its two bright siblings, which you can spot easily. Humanity did not even discover its own nearest neighbour until 1915. With a telescope, the star next door required an instrument to find. That is how deep the majority hides. Go back to the Texas desert one last time and look at those 9,000 naked eye stars with tonight's education. Who are they? Almost everyone is either a rare hot heavyweight, or a giant in a late blazing stage of life, or one of the tiny handful of ordinary stars sitting practically on top of us. The sky you can see is a gallery of exceptions. The constellations are drawn entirely from the top few percent of the population, and that is why the second lie from Chapter 2 mattered most. The night sky is an election in which only the rich are visible. Judge the universe by what shines, and you will misjudge it by a factor of 4, because the voters who actually make up the electorate emit almost nothing. Here is where this stops being a wonderful fact and becomes the central problem of the census. Recall where the count stands. For distant galaxies, we cannot count residents. We measure glow and convert glow into population. So ask the obvious question: who produces the glow of a galaxy? The giants. A single hot heavyweight star can outshine 10,000 red dwarfs put together. Photograph a galaxy at 40 million light-years, and essentially every photon in your image was emitted by the flashy few percent, the silent majority. The red dwarfs, who are most of the population, contribute a whisper to the total light. A galaxy's brightness tells you, with decent reliability, how many giants it has. It tells you almost nothing directly about how many dwarfs stand behind each giant. So the conversion from light to population needs a recipe. For every blazing heavyweight a galaxy shows us, how many mid-sized stars come with it, and how many red dwarfs? Astronomers call that recipe the initial mass function, the standard mix of star sizes nature produces when it makes a batch of stars. And it is, without exaggeration, the single most important ratio in this entire video. Every glow to population conversion, in every galaxy, across the whole observable universe, runs through it, measured here at home, in star-forming regions and clusters near the Sun. The recipe looks reassuringly stable. Lots of small, few big, in consist proportion. The same slope in every local nursery we check. If the recipe is universal, our conversions hold, and the census stands, and there sits the load-bearing wall. So name it plainly. Is the recipe universal? Does nature mix stars in the same proportions inside a giant elliptical galaxy as it does in our neighbourhood? Did it use the same recipe 10 billion years ago, in the violent early universe, when galaxies formed stars at rates we can barely imagine? For decades the field assumed yes, mostly because nobody could check. Then ways to check began appearing. Subtle fingerprints in galaxy light that betray the dwarf population, and some measurements of massive elliptical galaxies came back unsettling. They suggest those galaxies may be bottom-heavy, packing extra red dwarfs behind every giant, perhaps 2 or 3 times the standard allotment. The result is contested. The techniques are hard, and the field is actively fighting about it right now, which is exactly why you are hearing about it. If the ellipticals run bottom-heavy, then some of the biggest star vaults in the universe hold multiples of the stars we credited them with, and the total count shifts by literal trillions of trillions. The wobbliest link in tonight's whole chain is this one, the recipe. One more resident of the dark while we are down here, because she compounds the problem. A large fraction of what your eye, or any telescope at distance, files as one star is actually 2, Stars love company. They form from collapsing clouds that routinely fragment, leaving pairs and triples locked in mutual orbit. And among Sun-like stars, roughly half have at least one companion. Across interstellar distances, the pair blurs into a single point of light. One entry in the catalogue, two stars in reality. Some companions reveal themselves only by wobbles, eclipses, or split spectral lines. Every population estimate tonight carries a correction for these hidden doubles, and the correction is a live percentage, another dial that moves the final number by respectable amounts depending on who last calibrated it. So, update the ledger, and this update is the one the whole night has been driving toward, because the numbers are finally big enough to answer the title of this video. Take the galaxy census, 200 billion to 2 trillion. Weighed by class. Convert light to population through the recipe. Carry the corrections for hidden doubles. Let the range breathe to cover the honest disputes, including the red dwarf question sitting under everything. Multiply it out. Stars in the observable universe. 10 to the 22nd power on the low end. 10 to the 24th power on the high end. In words, from 10 billion trillion stars up to 1 trillion stars, and there, at the top of that range, sits the famous number from Chapter 1, the septillion, a 1 followed by 24 zeros. You now know exactly what it is, the generous edge of an honest range, whose width is set, more than by anything else, by a single question. How many silent red embers stand in the dark behind every star we can see? The width of that range is the red dwarf question. Write it on the ledger in red ink. Hold on, though, because I know what a number that size does to an audience. It sounds like an ending. It is not one, and here is why. What you just watched us build is a preliminary count, in any census that deserves the name. A preliminary count means one thing. The audits begin. Ours faces 4 of them. 4 separate challenges, any one of which could move that number by factors that matter. First, definitions. We have counted all night without ever agreeing on what counts as a star, and the borderline cases number in the tens of billions per galaxy. Second, time. Our count mixes eras in a way that should bother you, and fixing it drags in the entire history of the universe. Third, a machine. The newest telescope our species owns has been reading the earliest chapter of that history, and what it found does not match what the models promised. And fourth, our horizon, sitting quietly inside the very title of this video, waiting to redefine the question itself. For OD, the number survives them, or it does not. First up, the definitions desk, and a case involving the bright star on Orion's shoulder that might already be gone. Audit number 1, definitions, and this one plays out like a courtroom, so treat it as one. Every census in American history has had to fight about definitions before counting a single person. Who counts as a resident? What counts as a household? The questions sound like paperwork, until you remember that entire congressional seats swing on the answers. Counting is never just counting. Counting is deciding what deserves to be counted, and then counting that. Our census is no different. For 12 chapters we have thrown around the word star as if everyone signed off on its meaning. Nobody signed anything. So, before the final tally can stand, 4 borderline cases come before the desk. And these are no technicalities. Each ruling moves the bottom line by trillions of trillions. Case 1. The failed stars. A star, at working definition, is a ball of gas massive enough to ignite sustained hydrogen fusion in its core. That is the entry fee. Squeeze enough mass together, somewhere around 8% of the sun's worth, and the core lights, and the object joins the club. Now the applicant at the door. Nature also builds objects just below that threshold. They form exactly the way stars form, collapsing out of the same clouds. in the same nurseries, and they arrive weighing 2, often 4, 6% of the Sun's mass, too heavy to file as planets in any comfortable sense, too light to sustain the fire. They glow, faintly and briefly, on leftover heat and a flicker of secondary fusion, then spend eternity cooling into the dark. Astronomers call them brown dwarfs, which is a polite name for almost a star. They are everywhere. Surveys of the solar neighbourhood keep turning them up. Cool, dim, drifting, some closer to us than nearly any star, and estimates for the Milky Way alone run into the tens of billions, plausibly far more. So, do they count? The ruling of modern astronomy is no. No sustained hydrogen fusion. No membership. The census counts stars, and brown dwarfs are filed under other, alongside planets and everything else that never lit. Accept the ruling, and then read what it just did into the record. One definitional stroke, and tens of billions of star-like objects per galaxy. Objects, born in the same litters as true stars, vanished from the count. Multiply across a couple 100 billion galaxies, and the definitions desk just erased a number comparable to entire chapters of tonight's census. Nothing in the sky changed. A sentence changed. Keep that in mind the next time anyone quotes you a cosmic statistic with confident precision. Somewhere under that number, a committee drew a line. Case 2. The dead. Star's end. A star like the Sun burns for about 10 billion years, then sheds its outer layers and leaves behind its exposed core. A white dwarf. An Earth-sized cinder of carbon and oxygen. Fantastically dense. No fusion left. Just stored heat radiating away for eons. Heavier stars go violently, detonating and leaving neutron stars. City-sized spheres of matter so compressed that a sugar cube of the stuff would weigh 1 billion tons. The heaviest leave black holes, which have stopped being objects in any everyday sense at all. Our galaxy is thoroughly haunted. Something like 10 billion white dwarfs drift through the Milky Way right now, along with hundreds of millions of neutron stars, the accumulated dead of 13 billion years of stellar generations. So, is a white dwarf a star? It was one, unambiguously. It is made of star. It still shines. Astronomy's honest answer is that it is a stellar remnant, a separate category, the way a census separates residents from a cemetery, with no disrespect to either list. Tonight's count, and every mainstream count you will ever hear quoted, means fusion-powered, currently burning stars. The dead keep their own ledger. Case 3. The unborn, deep inside cold clouds of gas. Right now, gravity is pulling knots of material together into objects heating toward ignition. A protostar can spend hundreds of thousands of years in that state, glowing warmly from contraction alone. A star in every respect except the one that matters at this desk. The core has not lit. The ruling follows the others. Not yet. The census counts the burning, so the maternity ward waits outside. In fairness, the numbers here barely move the total. Mere millions per galaxy at any moment. We rule on it anyway, because a census that goes sloppy at the edges cannot be trusted in the middle. Which brings us to Case 4, the strangest case on tonight's docket, and I have saved it for last because it refuses to stay a technicality. It is the door to everything in the final act. There is a bright star in the winter sky called Betelgeuse, the red shoulder of Orion, about 650 light-years away, and it is old, swollen, and due to explode any time in the next 100,000 years, which in stellar terms means imminently. Now run the scenario. Suppose Betelgeuse actually detonated 500 years ago, around the time Magellan's crew was crossing the Pacific. The light of that explosion, crawling toward us at the speed of light, it would still be about 150 years from arriving. which means tonight, this very evening, you could walk outside, look up at Orion, and see Betelgeuse shining steadily in its usual place, while the star itself has been gone for centuries. So answer carefully, because the census hangs on it. When you count the stars in tonight's sky, does Betelgeuse count? Your gut probably says no, it is dead. And counting the dead is a bookkeeping error. But sit with what you are actually proposing. To count only the stars existing right now, this instant, across the universe, you would need the current status of every star simultaneously. And the universe flatly forbids that knowledge. No information travels faster than light. The phrase, right now, stretched across 100,000 light-years of galaxy, let alone billions of light-years of universe, has no checkable meaning. There is no cosmic present tense that any observer, anywhere, could ever verify. The only universe available to us is the one delivered by arriving light. A layered composite in which we see the moon 1 second ago, the sun 8 minutes ago, Proxima 4 years ago, Andromeda 2.5 million years ago, and the deep field galaxies as they were billions of years before the Earth existed. So the desk issues its final ruling, and read it as a solution, because that is what it is. We count the universe as observed. Betelgeuse counts, dead or not, because in the only universe accessible from this address, it is shining. Every star count in this video, including the final one, is a count of the observable inventory. Each object tallied as it appears in the light now arriving. It is the only census we can observe directly, and cosmologists who model other definitions still have to build them on top of this one. But notice the enormous thing the ruling just conceded. Our count is not a snapshot of a moment. It is a stack of eras. Near history and deep history photographed onto a single sky. And that concession cracks open audit number 2 all by itself. If we are counting across time, then the count depends on how the universe's star population has been changing over time. Was the universe always making stars at today's pace? Did the stellar birth rate hold steady across 13 billion years? Or did it surge and fade? Because if the pace changed, then a census across time is a census of history, and we had better know what that history was. The answer is that the universe has a biography, with a wild youth in it, and the biography is written in a colour of light your eyes cannot see. Audit number 2, time, and this audit begins in a drawer in your own house. Every family in America owns some version of the same object. A drawer, or a box, or lately a phone folder, holding photographs of the same people at different ages. Flip through it backward and a life runs in reverse. The grey hair darkening, the kids shrinking, the wedding, the awkward teenager, the baby. Nobody in those photos is the same age twice. The album is not a portrait. It is a timeline, bound at the spine. The last chapter established that our sky is a stack of eras. Here is the gift hiding inside that strange fact. The universe hands us its own family album, automatically, and it files the album by distance. Look at galaxies 40 million light-years away, and you see the universe 40 million years ago. Effectively yesterday. Look 2 billion light-years out, and every galaxy in the frame is photographed 2 billion years back. Keep going. 6 billion, 10 billion, 12 billion light-years, and you are turning pages toward the baby pictures. Astronomers never have to guess how the universe grew up. They can inspect every age of it directly. Tonight, the whole biography spread across the sky in rings of distance. No other science gets a gift like this. Geologists dig for their past. Historians rummage through archives. Astronomers just look farther. And the past is still out there, mid-frame. So the question ending the last chapter has a direct, observational answer. Point the great telescopes at each distance ring. measure how fast the galaxies in that ring are forming new stars, and plot the birth rate against cosmic age. Astronomers have done exactly this, painstakingly, across decades of surveys. The resulting curve is one of the most important graphs in the science, and its shape is anything but subtle. The universe's stellar birth rate never held steady. The curve climbs steeply out of the cosmic dawn, rises through the first few billion years, and peaks hard around 10 billion years ago. When the universe was roughly a quarter of its current age, astronomers call that era cosmic noon, and the name is earned. At the peak, the universe as a whole was manufacturing stars at something like 10 times today's rate. Galaxies in that era blazed with construction, gorging on abundant gas, colliding, merging, lighting new stars in torrents. And from that noon, for 10 billion years since, the birth rate has done one thing: declined, smoothly, steadily, era after era, down to the comparative quiet of today. Our own galaxy currently assembles a handful of new stars per year, a boutique operation running on the fumes of what its youth once burned through. The universe you live in is the universe after the shift ended. The factory floor mostly cooled, the great production run receding in the album pages behind us. The peak of cosmic star making sits 10 billion years in the past, and everything since has been the long afternoon. That fact gets one sentence tonight, and it just had it, before this audit can close. Though, you deserve the honest complication, because the birth rate measurement itself nearly failed, and the way it nearly failed loops our whole investigation back on itself. The universe's busiest star factories turned out to be almost impossible to see. Stars are born inside clouds of gas and dust. Always. The dust is no bystander to the process. It is the nursery itself, and it wraps every stellar delivery room in a thick, light-swallowing cocoon. Recall the West Texas dust storm, the wall hiding our own galactic downtown. Star-forming regions are that problem at maximum intensity. At cosmic noon, when star birth ran 10 times today's pace, the factories were correspondingly dustier, and the visible light of their newborn stars, the very signal a telescope hunts for, was being absorbed before it ever left the building. Survey the ancient universe in visible light alone, and you systematically miss the busiest sites of the very activity you are measuring. For years, humanity's picture of cosmic history was dimmed by exactly this: a birth rate curve drawn only from the births that happen near a window. The rescue came from physics that will feel familiar by now. Dust absorbs starlight, but absorbed energy never vanishes. The dust warms, and warm dust glows, re-emitting the stolen light at far longer wavelengths. In the infrared, a colour of light your eyes cannot catch but instruments can. The cocoon, in other words, does not destroy the evidence. It launders it. Every hidden stellar nursery in the universe rebroadcasts its activity as an infrared beacon. And when astronomers finally flew infrared telescopes above our atmosphere and aimed them at the distant universe, the hidden half of cosmic history switched on. Whole populations of furiously star-forming galaxies, nearly invisible in optical images, blazed across the infrared sky. Only by adding that hidden ledger to the visible one did the true curve come into focus. The full accounting of cosmic noon, seen and unseen together. File that trick away. The infrared as the colour of hidden history, because the next audit belongs to a machine built entirely around it. So the biography is measured. What does it do to our census? 2 things, and they pull in a direction you might not expect. First, it explains who today's stars actually are. If most star-making happened billions of years ago, then most stars alive now are anything but recent products. They are inventory from the great production runs, middle-aged and elderly stock, formed at or before cosmic noon, and simply persisting ever since. The universe's stellar population is no bustling nursery. It is an enormous standing inventory with a trickle of new arrivals. Second, and this is the part that quietly stabilizes the entire census, the inventory barely depletes. Think about who dominated that inventory 2 chapters ago. Red dwarfs. 3/4 of everything. And red dwarfs are the great misers of physics, burning their fuel at a starvation trickle. A red dwarf can last trillions of years, hundreds of times the current age of the universe, which produces one of the strangest sentences in astronomy. No isolated red dwarf, anywhere, has ever died of old age. There has been no time. Since the first stellar generations after the cosmic dawn, every red dwarf left to burn in peace is still burning tonight. A few get swallowed in mergers or torn up by companions, but old age has claimed none. In 13 billion years, the flashy giants live fast and die young. Sure, but they were always the thin, bright minority, the census masses, the silent majority. Do not leave. The star count of the universe behaves like a ratchet. The great production era filled the warehouse. The long afternoon adds slowly, and almost nothing checks out, counted across the observable universe. The standing total is about as high as it has ever been. That is genuine good news for the number on our ledger. The preliminary count, 10 to the 22nd power up to 10 to the 24th, is no snapshot of some fleeting moment that will embarrass itself in an eon. It is the reading on a gauge that fills and almost never drains. Audit number 2. Passed. And the count came out sturdier for it, but the biography leaves one final obligation, and it points straight at the last unexplored territory of the night. The birth rate curve climbs out of the cosmic dawn. Climbs out of what? Exactly. The first pages of the album, the earliest galaxies, the opening chapter of star formation itself, sat beyond the reach of every instrument humanity owned. The deep fields hinted at that era in a few precious smudged pixels. The models extrapolated into it. The census, honestly labelled, wrote insufficient data across the universe's first few 100 million years and moved on. Those pages stayed sealed for the entire history of astronomy, waiting on a machine that could read faint infrared light from the edge of time. Waiting, specifically, on a gold-plated mirror the size of a house, folded up like origami, riding a rocket out of the jungle of French Guiana on Christmas morning. The first pages are open now. Audit number 3 is what was written on them, and it is the one audit tonight where the universe talked back. Audit number 3, the machine, and this audit starts on Christmas morning, December 25th, 2021, a launch pad carved out of the jungle in French Guiana, on the northeast shoulder of South America. Families across America are still asleep next to their trees when, at 7:20 in the morning, East Coast time, an Ariane rocket lights up the rainforest and climbs into a grey sky carrying the most expensive space telescope ever built. $10 billion, 25 years of work, and folded inside that rocket's nose cone, packed like a ship in a bottle. A telescope too big for any rocket to carry in one piece. A mirror, 21 feet across, made of 18 gold-plated hexagons, folded at the edges, a sunshield the size of a tennis court, pleated flat. Over the weeks after launch, on its way to that same quiet parking spot, a million miles out where Gaia spins, the whole observatory had to unfold itself, hanger by hanger, cable by cable, hundreds of separate mechanisms, every one required to work, none of them repairable if it failed. People who follow this channel know that story, and know the whole field held its breath for 2 weeks. Every mechanism worked. The James Webb Space Telescope opened its eye on schedule, and one detail makes Webb belong to this audit. The reason it exists at all. Webb was built almost entirely around the trick from the last chapter. It is an infrared telescope, chilled to unearthly cold behind its sunshield, so its own warmth cannot blind it. Designed to read the colour of hidden history, Partly that is about dust, the laundered light of the cocooned nurseries. Mostly, it is about something grander. The universe is expanding, and as light crosses billions of years of stretching space, the light itself stretches with it. Visible light from the earliest galaxies, blue and white when it left home, arrives here, shifted deep into the infrared, far past what your eye or Hubble's cameras were built to catch. The first pages of the family album are anything but dark. They are written in a colour no previous great observatory could fully read. Webb was built to read it. So in July of 2022, when the first Webb Deep Field was released, everyone on the project knew exactly what they were doing. It was the 1995 gamble. Run again. With a bigger mirror and the right colour of eyes. Point at a pinhead of sky. Stare. See what swims up. For the fourth time tonight. Put the deep field on screen. And this time put both of them up. On the left, the original. Williams' gamble. 3,000 galaxies. The image that started this video. On the right, Webb's version of the same kind of pinhead. Same sky. Same idea. 30 years apart. The difference hits you before any caption can. Webb's frame is drowning in galaxies. Objects that were faint smudges to Hubble resolve into spirals with visible arms, and scattered through the frame sit small red sources. Faint embers that appear in no Hubble image at all, because their light arrives entirely in colours Hubble could never see. Among those red sources are candidates from the universe's earliest known chapters, galaxies whose light set out during the opening few 100 million years. The first pages, photographed at last after the entire history of astronomy spent wondering what was written there, and almost immediately, the writing said something nobody expected. The predictions were specific, decades of theory, tuned on Hubble's hints, described how the first galaxies should look. The universe's opening few 100 million years were supposed to be a modest era. Small, faint, fumbling proto-galaxies. The first sparks catching, star formation clearing its throat. Webb should find those first sparks. Dim and few. Webb found floodlights. The early universe came back more crowded than predicted, and more grown up. Galaxies at the edge of time proved more numerous than the models called for, and many are startlingly bright, some looking disconcertingly mature, organised, massive, at an age when the universe was barely out of the delivery room. Record holders started falling within months. Teams kept confirming galaxies deeper into the first pages, and by the middle of this decade, the confirmed champions included a galaxy called MOM-Z14. Its light dispatched when the universe was roughly 280 million years old, 2% of the universe's current age. The cosmic equivalent of finding a fully lit city in a baby picture. You have watched enough of tonight's investigation to guess what happened next in the press. Headlines announced that Webb had broken cosmology, that the Big Bang was in trouble, that everything astronomers believed was wrong. And this is where the measured truth turns out smaller than the headlines and far more useful for our census. Nothing fundamental broke. The expansion of the universe. Its age. The Big Bang framework. All of it stands, tested by mountains of independent evidence. What Webb genuinely did was catch our assumptions being lazy at the one link in the chain with the least data behind it. The models of the first few 100 million years were extrapolations, educated guesses projected into an era nobody had ever photographed. Webb photographed it. The guesses ran low. Now, the honest question for our ledger, does that push the star count up? Be careful here, because this is exactly the kind of moment where an investigation earns or loses its credibility. More early galaxies. Brighter early galaxies. Sounds like more stars, and it might mean that, but brightness is testimony, and testimony needs cross-examination. Those early galaxies could be brilliant, because they hold more stars than predicted. They could also be brilliant because they forge stars in short, violent bursts that flatter a survey, or because their first stars were individually heavier and brighter than today's, in which case the same light testifies to fewer stars, or because some of that light comes from matter crashing into central black holes, which are no stars at all. The field is arguing about all of these right now, in the journals, this year. So the disciplined verdict of audit number 3 reads like this. Webb has raised the pressure on every model of the early universe, and it has proven that the faint end of the first pages holds more entries than the old extrapolations assumed. Whether that ultimately nudges the final star count toward its ceiling depends on why those galaxies burn so bright. And that answer is still being written. The audit does not overturn the number. It marks one corner of it, the deepest corner. As live and under revision, take one last look at the pair of images before leaving this chapter, because they close a circle 30 years wide. In 1995, a man bet 10 days of telescope time that an empty patch of sky was hiding a universe. He was right. 3,000 times over in a single frame. 30 years later, a telescope with better eyes stared at the same kind of emptiness and found even more than the gamble revealed. Twice now. Humanity has aimed its best instrument at certified nothing and been overrun. Every floor we have ever stood on turned out to be a ceiling for someone below. 3 audits down. Definitions. Ruled. Time. Past. Webb. Live but contained. The chain is as complete as this generation can make it. Every link forged. Every link tested. Every wobble measured and labelled. Time to build the number. Every great construction project ends with a walkthrough. The inspector shows up with a clipboard, and the builder walks the building, floor by floor, pointing at what was done and how it was verified. Tonight, you are the inspector. The final number goes together in front of you, one floor at a time, and at every floor you get 2 things with equal honesty. What holds it up, and how much it can sway. Floor 1. The galaxies. We count the bright ones directly. In deep fields certified boring by repetition. Multiplied across a sky that measurement says runs the same in every direction. Then we correct for the dim majority below every camera's floor, using the population's measured shape, cross-checked by gravitational lenses that let us see below the mesh, and audited by the darkness of the sky itself, read by a camera beyond Pluto. The result? Somewhere between 200 billion and 2 trillion galaxies in the observable universe, with Webb's crowded first pages keeping the argument alive at the far end. Sway, roughly a factor of 10, and we know exactly which floorboards flex. The faint end. Always the faint end. Floor 2. The stars within them. Residents cannot be counted at galactic distances. So light gets converted into population. The glow of each galaxy reports its blazing few percent. And the recipe, the initial mass function, testifies to how many quiet residents stand behind every bright one. That recipe holds steady in every nursery we can check directly. Its sway lives in the places we cannot check. The giant ellipticals that may run bottom-heavy with extra dwarfs. The violent early epochs that may have mixed a different batch. Fold in the weighing of galaxies by class. Sheds counted as sheds. Towers as towers. Giants as the 1,000 Milky Way monsters they are. Fold in the hidden doubles. Companions blurred into single points of light. A live correction of respectable size. Floor 3. The rulings. Fusion-powered stars only. Brown dwarfs turned away at the door. Tens of billions per galaxy. Set aside by definition. The dead filed on their own ledger. White dwarfs and neutron stars alike. The unborn waiting outside, pending ignition, and the whole count taken the only way it can be observed. Each star tallied as it appears in the light now arriving. The stacked eras of the one sky available from this address. Floor 4. The biography. The count is no snapshot that history will embarrass. Cosmic noon filled the warehouse 10 billion years ago. The long afternoon adds its trickle, and the silent majority never leaves. No isolated red dwarf has ever died of old age. The gauge fills and almost never drains. The number about to be stated is about as large as it has ever been, and it will hold for eons. Now run the multiplication. Honestly, carrying every range we measured instead of collapsing them into false confidence. 200 billion to 2 trillion galaxies. Populations weighed by class and converted through the recipe. Corrections for doubles. Rulings applied. Biography integrated across the observable volume. Out comes the number this entire night has been building. Between 10 to the 22nd power and 10 to the 24th power stars. In words, at the floor, 10 billion trillion stars. At the ceiling, a trillion stars. A 1 followed by 22 zeros. Up to a 1 followed by 24 zeros. And there at the ceiling, exactly where Chapter 1 found it, sits the famous septillion. You now hold its birth certificate, neither a measurement nor a guess. The honest upper edge of a range assembled from a dozen instruments and a century of method. Its width dominated, above everything else, by the oldest suspect in tonight's file, the dim ones, the stars and galaxies below every line we have ever drawn. Update the ledger one final time, and let it stand complete. Stars in the observable universe, 10 to the 22nd power to 10 to the 24th power, and beneath that towering figure, keep the first entry from the start of the night, because the pairing is the entire story of this video. Stars individually measured by our species. About 2 billion. Look at those two numbers sharing one screen. 2 billion. Counted one at a time by a patient machine a million miles from home. 10 to the 24th. Built above it by inference. Floor upon floor upon floor. 14 orders of magnitude apart. And every story of that tower inspected tonight. Sway and all. One item remains on the clipboard before the fourth and final audit. The number owes a debt to an old and beloved claim. One you have heard your whole life. One this channel refuses to repeat without checking. It involves every beach on Earth. You have heard the claim. Everyone has. There are more stars in the universe than grains of sand on all the beaches of the Earth. Carl Sagan made it famous more than 40 years ago. And it has been repeated in every classroom, every planetarium, every space documentary since, almost always with the same reverent tone, and almost never with a single number attached. Tonight the claim gets its audit. This channel does not repeat claims it has not checked. Start with the sand, and be deliberately generous, because a claim this famous deserves to face the strongest possible opponent. A grain of beach sand runs roughly 0.5 millimeter across, which packs about 8 billion grains into a single cubic meter. Now build the world's most flattering inventory of beaches. Take every mile of coastline on Earth, hundreds of thousands of miles of it, and award every single mile a sandy beach 50 meters deep and 10 meters thick. Far more beach than most coastlines actually carry. Enough to cover the sandbars and dunes behind them too. Run the multiplication. The volume comes out around 100 billion cubic meters, and the grain count lands near 10 to the 21st power, a 1 followed by 21 zeros. Stricter definitions of beach, the kind geologists actually defend, come in 1,000 times lower. So the sand of planet Earth, counted with maximum generosity, tops out around 10 to the 21st grains. Set that beside tonight's number. Stars. 10 to the 22nd up to 10 to the 24th. The audit verdict is in, and the famous claim survives, even handing the sand every advantage, even inflating the beaches of Earth beyond anything the coastlines really hold. The stars win by a factor of at least 10, and at the ceiling of our range, by a factor of 1,000. Under the stricter sand counts, The margin stretches far wider still. Walk any beach in America. Scoop up one handful, and the grains running through your fingers are outnumbered, comfortably, by the stars in the sky above them. Sagan's old line was never poetry pretending to be math. It was math that happened to sound like poetry. The oldest comparison in astronomy. Audited and confirmed. It may retire with honours, and with the number stress tested, one final question remains on the clipboard, and it has been hiding inside a single word of this video's title all night. Audit number 4. The horizon. And this one begins with a confession about the title of this video. The title asks how many stars exist in the universe. 17 chapters in. It is time to admit that one word in that sentence has been quietly doing sneaky work all night. The word universe. Every number built tonight. The galaxy counts. The deep fields. The 10 to the 24th ceiling. Describes something astronomers are always careful to call the observable universe. We flagged that definition back in chapter 1. Now you get to see what the adjective is guarding, and why the guard matters. The setup is simple. Light is fast, but not infinitely fast, and the universe has only existed for about 13.8 billion years. Put those two facts together, and they build a wall. The only objects we can possibly see, even in principle, even with a perfect telescope, are the ones whose light has had time to complete the trip. Anything so far away that its light is still en route, needing more travel time than the universe has existed, is simply absent from the sky, neither hidden nor faint, absent, with no workaround, because the information has not arrived and nothing outruns the information. That wall wraps around us in every direction, enclosing a sphere, our sphere, the portion of everything whose light has managed to reach the Earth. You might expect the sphere to reach 13.8 billion light-years in radius, matching the age, but the universe has been expanding the whole time the light was travelling, stretching the road behind every photon as it flew. So the sources of the oldest light we receive have by now been carried much farther out. Run the accounting properly, and the observable universe measures about 93 billion light-years across. That is the arena of tonight's census. Everything we counted lives inside that sphere. Now the question a child would ask, which happens to be the deepest question in this chapter: what sits outside the sphere? First, be clear about what the edge is not. It is no wall of the universe. It is a limit of delivery. The horizon is defined entirely by where we happen to stand and how long light has had to travel. An observer in a galaxy at the edge of our observable universe owns their own sphere, centered on them, reaching 93 billion light-years in every direction from their address, including deep into territory we can never see. Their sky is full of galaxies missing from our sky. The edge moves with the observer. Think of standing on a dark ocean at night with a flashlight. The circle of lit water around you is real, and it is yours. But the rim of that circle is the range of your flashlight. It was never the edge of the sea. So the honest expectation is that beyond our horizon, the universe simply continues. More space, more galaxies, more stars, unrolling past our delivery limit. And remarkably, real evidence points that way. First, everything visible, right up to the horizon, is uniform. The same density of galaxies, the same physics, the same kind of universe in every direction, with no gradient, no thinning, no hint that an edge of anything is near. If we sat close to some cosmic boundary, the view toward it should differ from the view away from it. It does not. Second, the geometry of space itself. Cosmologists can measure whether the universe curves, because curvature would distort the sizes of features in the oldest light in the sky, and those features have been measured with exquisite care. The verdict keeps coming back the same: flat as our instruments can test. And flatness carries an enormous implication, because a strongly curved universe can close on itself into a finite volume, while a flat one, in the simplest reading, just keeps going. Be careful with that conclusion. Though, flatness alone does not prove infinity. A flat universe can still be finite if it wraps around on itself in ways our measurements have not yet ruled out. The honest options run from vastly larger than our sphere all the way to literally infinite. And current science cannot pick between them. That is no gap in effort. Information from beyond the horizon cannot reach us. So the question sits outside measurement itself, at least for now, and possibly forever. Watch what this does to the title question. If the universe means our observable sphere, tonight's answer stands 10 to the 22nd up to 10 to the 24th stars. Measured, corrected, inspected. If the universe means everything that exists, the answer multiplies by some unknown factor. And if space truly runs infinite, the count of stars has no ceiling at all. There would be, in the fullest sense, no number. The final audit closes on the strangest finding of the night, delivered plainly, as a measurement and nothing more. Our sensors counted everything light has ever delivered to this address, and it is magnificent, and it may be the smaller share. Tonight's number was never the count of all there is. It is the count of all that can ever be known from here. For audit, definitions, ruled, time, past, Webb, live but contained, horizon, labelled. The clipboard is clear. 18 chapters ago, this video promised a real answer, earned link by link. Time to sign the census. We open tonight with a man betting 10 days of the world's greatest telescope on an empty patch of sky. The question that gamble forced on us has an answer now, and you have personally inspected every link in its chain. So here it is, the way an honest census delivers it. 3 answers, in 3 layers, each one truer than the last. The first layer is the public answer, the one for the classroom and the dinner table. In the observable universe, there are up to about 1 septillion stars. Say it in full. Once. Slowly. 1 trillion trillion. A 1. Followed by 24 zeros. Divide that number among every human being alive, and each of the 8 billion of us receives over 100 trillion stars. That is the headline figure. And unlike most headline figures, you now know it carries a birth certificate. The second layer is the working answer, the one astronomers actually use. The count is a range, 10 to the 22nd power up to 10 to the 24th power, and the width of that range is the measured size of the remaining ignorance, every piece of it carrying a name and a file, the dim galaxies below the mesh of every deep field. The recipe question: how many silent red dwarfs stand behind every blazing giant, especially inside the great ellipticals, the hidden doubles fused into single points of light? The crowded first page's Webb is still reading. Name the disputes, and you have named the distance between the floor and the ceiling. That is what a real scientific number looks like with its clothes off. A range, with every source of doubt labelled and under active attack. And the third layer is the deepest answer, the one this entire investigation was built to deliver. Nobody has ever counted the stars. Our species has individually measured about 2 billion of them. Everything above 2 billion, every zero from there up to 24, is inference, and you have now walked every floor of it yourself. A pulsing star in a glass plate archive, timed with a calendar by a woman paid 25 cents an hour, becoming a ruler that reaches across the universe. Red ink on a photographic plate on a freezing California mountain. 10 days of telescope time gambled on certified nothing. Twice. 30 years apart. And overrun both times. Fish math. And a definitions desk. And the darkness of the sky read by a camera beyond Pluto. And a birth rate curve recovered from stolen light. 2 billion measured stones. and rising above them a tower of verified reasoning 14 stories of zeros tall. Every floor built by someone who refused to accept the floor below. So the next time you find yourself somewhere genuinely dark, out in Big Bend or up some mountain road, and the sky opens over you, here is what you will know that almost nobody standing next to you knows. You are looking at a sample, 9,000 stars at the absolute most, every one a giant or a neighbour, the flashy top slice of a population that is 3/4 invisible embers. Behind them, a galaxy of hundreds of billions you will never see. Behind it, hundreds of billions of galaxies, most too faint for any eye, any camera, any instrument ever built. The night sky never showed anyone the universe. It showed a preview, and let us earn the rest. A trillion stars, give or take a healthy argument, counted from a planet whose own people have directly met 2 billion of them. Every zero in between was earned the same way, by somebody, somewhere, refusing to stop counting. Thanks for watching. If this investigation earned your time tonight, a like and a subscribe genuinely help the channel. And tell us in the comments which number from tonight is going to keep you up. There are about a septillion to choose from.